Yeah. Hello, welcome to Emma Monday. We are not in the normal place because
The live stream failed.
the live stream failed.
We're re-recording our AI explainability with biomedical imaging talk, which
Yes.
is a collaboration with the Biomedical Engineering Society.
Yep. So today we're basically gonna start with neural networks, how they work, and then from there we're going to go on to transfer learning from Gabe and why that's important. Then we're going to go on to AI explainability, and then we're going to show you our sort of implementation, which we aren't going to do today because that's the one thing we got live streamed. So, yeah. So let's start off with what are neural networks. So I'm sure you've seen a basic neural network before. This is what you'd see on like a stock website where they try and use every known hook word possible. But as you've seen this one before, I'm going to show you guys this one. So basically, this is a neural network and how it works. So basically, a neural network can be formed using inputs and outputs. So this neural network tries to map some number of inputs or list of numbers, which are most of the time a list of numbers, and you give it a list of numbers x is what we're going to call it, or these sort of inputs. You're trying to map some function f that can map the sort of inputs into outputs. And since these sort of images can be broken down into lists of numbers, you can kind of see that I'm alluding to convolutions later. Weights and biases. So lines in this diagram are weights, these here, and this scales the function. So it moves the function like left and right and so on. We scale, so in like a function or math sort of representation, this function scales the input by w and then it equals y. And then so these circles here are biases, and this helps shift the function left and right. And in a function, a representation, we have the plus b on the end there. That's about it. The activation function. So the activation function tries to fit these sort of inputs and outputs, and it's kind of like the shape of the function. And this represents the actual function itself, like how the inputs are being mapped to the outputs. And there are many different types of activation functions. One of the most common is ReLU, or rectified linear unit. Another one is tanh. This basically just scales numbers between -1 and 1. And the third one is a sigmoid. This basically just scales of any value x into a value between 0 and 1. There are many more, and I linked a Medium article down here. You can't see it, but in the link in the description, there's a presentation, and all the links and sources are linked in there. So changing the weights. What does changing the weights do? So basically, changing the weights makes this function go, so like this red function become less confident, and when you increase the weight, this blue function becomes more confident. And in this actual thing, so we change f from our last mathematical representation to this sigmoid because it helps map what the function actually looks like. So this weight w and the input x, so the math representation of this would be sig wx, and then when you change these weights, this is what it looks like. Changing biases. So when you change the bias, it shifts the function left and right. We use the same activation function, same weight, but instead we add that bias on the end. And when we add the b, you can see it shifts the function left when it's positive and right when it's negative. It shifts left because it's positive, simply because when you're solving for y, you basically minus it on the other side. So the whole picture. So basically, if you have a bunch of layers of these and you solve for a bunch of weights and biases, you can essentially make anything into a linear equation. But how do we learn these weights and biases? Well, through backpropagation. And there's other methods, but not in this lecture. So the basic idea behind backpropagation at like a high level is there's basically like 4 main steps. First, you have to define the loss function. The loss function is essentially the actual minus the predicted. And since the predicted itself is actually a function, you're basically doing a constant minus a function, which itself is a function. You basically then go in and you calculate the magnitude and the direction of the derivative of that loss function, of where that sort of input is on the loss function currently on the weights and biases. And then you essentially want to find the place where it's going the most negative and choose that direction, but then you multiply that direction by a learning rate. So the learning rate basically determines how far away you're moving, how much you're moving those weights based off of that loss in that direction. And when you change the weights and biases of your function, you basically go in there, you change it, based off of the derivative or Jacobian, if you want to look it up, of that matrix, and then its learning rate. You repeat, and then you go to the next epoch, where a sort of epoch is an entire set of data, and a batch is one example of backpropagation, and then you basically average those backpropagations over on an epoch. So a more realistic function looks something like this, where loss functions are generated every batch. So starting here, we want to get here. So essentially there's a bunch of local minimas, and one of the things that's bad about gradient descent is that it doesn't really know when it's a local minima or a global minima, which is something that other sort of algorithms can account for. So how is image data stored? So image data is stored like this, where it's just a list of pixels, RGB, each having their own set of pixels. And we have this dog. So this is a picture of a dog. You add those, you slice those all together, and you get something like this. Finally, convolutions. So convolutions are this kind of a sequential thing where each of these values in a filter go through, and they filter out the pixel data. So this is an example of a convolution. If you look at the slides, this might be hard to read. If you go through, you can multiply the filter with its corresponding value, and then you add them all up, and you get -7. So essentially, you take the result of this element and you take the sum. So it's just like in the neural network, you take each node in the network and you multiply the weight and add the biases to all the terms, and then you get the sum. So multiplying, adding, and summing is pretty much all of machine learning going forward. It's pretty much, and then edge detection example. So if you change the filter, you can get something like this, where you have a filter that goes through and it finds a bunch of edges. So here's an example. So here's an example of what it kind of looks like going through. And then, a thing to note is that typically you want your filters to add up to 0, because then you're not adding or removing any data, technically. That's the result. So there's a big difference between machine learning and deep learning. So machine learning is where you have an input and you take the feature extraction step and you do the classification. And then that classification has an output. So like there's a bunch of features predetermined from your sort of input. But instead, deep learning only takes the input, and it has enough data where it can do the feature extraction step on its own. And that's where convolutions kind of come in, where a convolutional neural network has that feature extraction step of going through and doing a bunch of filters. So what does this do? So you basically have this convolution that goes through and finds those values. Once you have those values, you can do a 2x2 pooling, which essentially just takes the result of your convolution, creates a 2x2 matrix, and then just chooses the largest value. These are really good for classification tasks, but if you're doing something more like a regression tasks, a sort of instead of a max pooling, you would use something more along the lines of a pooling that's you would do something more along the lines of an average pool. I don't know why those words weren't coming out. All right, so now to Gabe with transfer learning.
All right, and so transfer learning, it is using general pre-trained neural networks for different domains and tasks. One example is very popular in image or computer vision tasks is the neural networks trained on the ImageNet dataset, of which there are many. And the reason why it's very popular to do transfer learning is because it offers a lot of advantages. So because you're not training from scratch and you're using a pre-trained network, the only thing you have to change is the part of the neural network that you use for your specific task. So that means there are less parameters because the pre-trained neural network has been fully trained. So this results in a lower training time. Furthermore, since you have less to train on when you're fine-tuning for a specific domain or task, you need less data to get as performant results. For example, the ImageNet image corpus consists of 1.2 million images with over 1,000 classes, and so the convolutional neural network that's pre-trained on that learns a representation of all of those 1.2 million images, and you can leverage that knowledge or the extracted features that pre-trained neural network has learned for your own task. And so you need much less data to get pretty good results in terms of accuracy. And again, because of this, using the general pre-trained networks, you can utilize this knowledge that the existing models have already learned, and you don't need to, that you don't need your own model to learn from scratch. Some examples of pre-trained convolutional neural networks. The first one that really came into the foray was VGG19, and the next one is ResNet 50, and that's the one we had used in our demo. And newer ones such as Inception V3 have been created as well. It has a bit more complex architecture, but overall it has less parameters and outperforms both VGG19 and ResNet 50. And so in computer vision, there's always a lot of papers that are creating new architectures to see their performance, such as top 1 accuracy and top 5 accuracy on standardized image data sets such as the ImageNet corpus or something like COCO. Yeah. As you can see here, it's all trained on the same data set, the ImageNet data set, which is 1 million images of 1,000 different classes. And so why this is important is because, again, the convolutional neural networks extract features and make it easier for the computer to understand what it's looking at. And so it has an understanding of the content of the image rather than just the raw pixel data from the image. And because the pre-trained neural network has already extracted those features, we don't need to do that, and we can leverage what it has already extracted for our own purposes. And so what we do in our implementation of transfer learning is utilize a ResNet 50 backbone and add this classification head to predict the specific classes that we want. One specific example is from predicting from an X-ray image of a chest whether or not a person has pneumonia. And so rather than using the classification head of ResNet 50, which would predict the 1,000 images it's trained on, we replace that with our own classification head that tries to predict whether or not someone has pneumonia based on the CT image. And so only this part outside of the backbone is getting trained because the ResNet 50 layers, their weights are already frozen. And so in the most basic form of transfer learning for computer vision, specifically image classification, you take the backbone, freeze these layers, and then add your own classification head for your specific task.
All right. So for the sort of AI explainability portion, we used this paper called GradCam from 2016. I linked the paper and the GitHub in the presentation. And as you can see, based off this original image, when the model predicts dog, it weights the dogs within the convolution a lot, the place where the dog is. And when it predicts cat, it weights from the convolution where that cat is. And you can see this is like a heat map where red is a really high weight and it kind of dissipates around. There's some other cool visualizations you can do with GradCam, but I think this one's the most compelling, the heat map. And this guided backprop basically gives you back the means of what comes back, and then this is like the standard deviation, where if a convolution, if you think about a convolution as like a covariance matrix, then you can figure out the weights or the biases in the covariance matrix and how it distributes the weights on the input image. So for GradCam, there's a bunch of things you can use GradCam for. The one that we used it for is this sort of classification of an image. And essentially what it does is, like I said, it takes those gradients back and it finds where the weights, where like the means are for what it would predict cat. And then it essentially generates that heat map based off of those means and variances, and the variances from the convolutions. So this is the implementation. So we're gonna give it back to us in the past. Please. Hey, what's up, guys? Sorry about that. Kyle here again. So basically, I forgot to talk about this in the last one, so we're just going to talk about it now. Sorry about that. So for our results, the first results are for CT imaging. Here you're going to get access to the notebooks. You see I can click here, go back to it. This is the notebook we used for training. For this one in particular, the other ones don't have this same quirk, but this one in particular, you have to click this top part, but you can still come in and see it. You have to download this data set and you can run it as long as you throw the data set in here. So you can see the results, but I have this all out now, so here we go. So the results. The results for this were pretty good for the CT scans. Gabe trained these, and as you can see, the attention on this side over here, they have a good heat map, and you see like these different classes, and you could tell by the loss function that we're not overtraining, and this confusion matrix turns out good. So you can see like it's paying attention to the right spots for these different types. So the reason it's red here for normal, where these spots are actually supposed to be, is because large cell carcinoma is good in the middle, but for things like squamous cell carcinoma, I actually don't know. I'll be honest. These look like good results, but I honestly don't know. I'm not an expert. But essentially, if you were to consult an expert, you could show them these and they could tell you whether or not it's making a good prediction. That's the basic idea. The results for this are the loss. So you can see that this loss isn't really overfitting, and you see this confusion matrix here. You see that it's mainly whatever the true label is, it's predicting the predicted label. Our second results are the X-ray imaging. Same thing here. You go to the training notebook and you go to the testing notebook. This is where in the testing notebook we link you to models. So basically you can go to this folder and then you can put in these models into the notebook and it'll work. So these are the results for the X-ray notebook. So as you can see, when we throw the notebook for the X-ray, you can see that it's not having the attention in the right spot. So what the hell happened? What the hell just happened? What the hell? So basically, this is an example of overfitting. So I didn't do this on purpose. I'm not going to cap, But when I saw that it was overfitting, I thought that would be a good idea to show what this would look like when it was overfitting, just to see, give you guys an example of what it would look like if it was overfitting. And you could tell that since all the convolutions are over on this right side, that it's working like that. And you can see that when we test it, it doesn't get good results. Makes sense, right? You know, it's overfitting on this side. So what actually happened? What actually happened? I think what happened was that the model decided that it was easier to figure out the shape of this side of the body to determine which patient it was than it was to actually find the pneumonia in the lungs. And without GradCam, we would just have an accuracy of still about 80%, right? But the problem is 80% in medical is really bad. Like if you like any 1% of people that you miss pneumonia on, they could die. So the stakes are really high. But yeah, I just wanted to give that example, and thank you. I'm gonna actually now put it on to Pass Me. Thank you. This is me answering questions that they asked after seeing all this data. Thank you.
Arms as the entire kind of code runs.
Yeah. So this is the result. You see that? How all of them are on that right side. Except for like these, but these came back. So this one actually came back as the correct result, and it has more in the lungs, right? So this one, so everything past this should be class normal. Oh wait, no, never mind. Hold on. Everything past, so yeah, so normal, yada yada. Yeah. So you can see it's all on the right side. I mean, these results are kind of like just useless at this point. But the thing is, it got a really good score on the test set. So if you go up here. It got a decent score on the test set of like 80-something%, right? Yeah, 83% on the validation set. But it's if you just go by the validation set, you aren't like looking at overfitting. You could, deploy a model that's just checks to see what the shape of the arms of the patient is, not whether or not they actually have pneumonia. But yeah. Gabe, you want to go over the code a little bit?
Yeah, there's a question.
Oh yes.
If you crop the image to not include like the bend of the arm, would it have a better accuracy?
Yeah, but how do we know where to crop the image? So we know that all the data we need is in the image already, right? But how do we figure out where to crop that image so the arm's not in there?
Another network.
That's actually I've come across that problem many times in terms of image classification and computer vision. And the best you can do is come up with a heuristic. So like if you want to say cut off the arms from the image, just reduce the image, like cut off those image by like, 20 pixels. And it's not going to be the same for everyone, but that's as good as you're going to get.
Yeah.
At least without doing a lot of things like you don't want to use AI.
Yeah.
Can you just determine it by the torso? So like where the black changes to white, and then that would be like the cutoff.
You could.
Yeah.
I've done like edge detection methods for transforming images or filtering images.
But then you also run into the problem. Sorry. But then you also run into the problem where all the images are different sizes, so you don't have like a set number of things for the actual prediction. Does that make sense?
Yeah.
Okay. Yeah, but that's a good question. I mean, that you could do that, and in general, you want to take the data set you originally have and change it as little as possible, because then that's the best representation of the data that you're ever gonna get is that original data. Yes.
One thing when they're taking medical images now, like X-ray, CT, whatever. A lot of them now are introducing like a radiopaque kind of boundary of where you want to focus your image at. So like what you were talking about with the edge detection, they would provide images with that like already boxed area where you want to be. So it would just be really quick to cut everything else off outside of that box. But a lot of the images you will get right now don't have as clear as data, so you just kind of have to go with it as it comes.
Yeah. And in actuality, the best solution is to just change some hyperparameters and make sure that you're not overfitting, you're not going over too many boxes.
Next week.
There's
Yes.
also like
So, by the way, next week we have a professor from UF actually talking about how to do that. She's a really good professor. Yes.
Yeah,
Jen.
there's another angle of this that I think is important to explore. Do you have like the accuracy printout?
Yeah.
Like in the notebook.
Yeah, I have this one. Or do you want the other
Or
one?
yeah, like in the notebook where you're printing out the accuracy is about 80%.
Oh yeah.
Yeah, you know what I mean.
Here?
Yes, exactly. Okay, so you see like the validation accuracy is pretty high, and you might think like, oh, the model's about 83, 84% accuracy. This must be pretty good. Well, let's consider the problem of like you go into the hospital, right? And 90% of patients are fine, right? 90% of patients don't have disease A, and 10% of patients do. And let's say I, as a doctor, just predict that every single patient is normal. What's my accuracy?
90%. Sorry.
Oh, how'd you figure that
Sorry,
out?
my bad.
Yeah, so the accuracy is 90%, right? Even though I'm not doing anything, like I'm not considering any of the patient's like data at all. And if I just guess 90%, guess the patient is always normal, I get an accuracy of 90% without doing anything and while being completely wrong. This is a terrible model. And the reason for this is that the data is highly skewed. Most people don't have the disease, and a small number of people do have the disease. But it's really important that when someone has a disease, that we get it right. So this is known as like unbalanced classes, skew, and other names. And when there's skew or unbalanced classes, it's pretty common to have very high accuracy, but actually a terrible model.
Yeah.
So accuracy is actually not the best metric to use in this case. There's another metric known as F1 score that you can probably look into if you're interested in what to do there. But
Yeah.
Unbalanced classes are really common in medical imaging because like the number of patients who have cancer is going to be much smaller than the number of patients who don't have cancer. But it's really important that when a patient does have cancer, you get it right.
I had the same experience as that. I was building a model to like predict MMA fights, and every time you would have a heavyweight, it would always predict a knockout because the percentage is so high. It just figured, hey, if I just predict knockout every single time, I'm likely to get it right.
Yeah. Nice.
But
Yeah, no, this stuff like this is a balancing act, and it's really important that you understand why it's getting the results that it is.
Yeah, you want to show the ROC stuff you worked on?
Yeah, so the way that I kind of figured this out, how to make it a little more accurate, was I did this thing called receiving operating characteristic. So basically, what this does is it says so this x here would be like the false positive rate, and this y here would be the true positive rate. Okay, so if we were to randomly guess, it would just be a linear equation here. Right? So it's better than a random guess, but it's not very good. But essentially what this does is it takes, so for example, this threshold, and it takes those weights of that threshold, and it tries to figure out, okay, if it's above this threshold, and I have like my score, my confidence, and I move that threshold around, can I get a better false positive rate or true positive rate, right? So essentially what you do is you take this false positive rate and you find where that false positive rate or true positive rate is the highest. So you basically take TPR minus FPR on all of them and you get the highest value. So in this case, the threshold like 0.98, right? So you take this threshold and then you essentially, and to ensure that this score is actually good, you do an AUC score. I forget what this is called. To be honest. Oh yes, the sort of, it's just the sort of area under the curve. So if I were to draw this ROC line here, I was going to go to the board. If I were to draw this line here, it'd be the area under this curve that you draw here, right? So then so base is 1. If it's 0, then it's just about the same as random choice. And then you basically, so now I pick this threshold. I choose 98 because that's what the best threshold was, or the furthest from random guess. And then I just create this thing called get class. If scores greater than the threshold, you get the Y prediction threshold. And then essentially you create this Y threshold that's just, if it's greater than what we said, then it goes, and it basically resets, and you get a much better model. Does that make sense? And I think the reason this score has to be so high is because all the weight is going to that right side, and very little weight is going in the actual middle. But what it has in the actual middle is working. Does that make sense? So that's a very common feature of overfitting. You can run an ROC score and it gets a good score, and you can figure out where that threshold is. Just if you guys have if it took weeks to train a model and you don't want to retrain it, you can do this. You can do this. Took like 7 hours to train. So, but yeah, yeah. I mean, so do you want to talk about the code? Go through it a little bit.
So
Here you can.
yeah. So for the implementation of transfer learning, so you're good.
There you go. Go for it.
Yeah. So there's a pretty predefined sort of like pipeline you kind of have to go through, and most of it is data. So I'll walk you guys through it a bit quickly. So first, you define the transformations you want to do on the data. So what this does is, this is image pre-processing before the network, and PyTorch has a thing where you can just input a list of the transforms. So what we're doing here is just resizing it to 305 by 430 pixels, transform it to a PyTorch tensor, and then since we're using ImageNet, these values, these hard-coded constants, are ImageNet means and standard deviations. We're normalizing it because we're using the ImageNet weights for the transfer learning. And so then we create the data sets by specifying the folders. And
Oh wait, can you go show them the folder structure really quick?
yeah, is it loaded in this one?
Oh, it might not be actually. Oh.
Yeah.
Okay, but you can kind of show them from there. So.
Yeah. So the root data directory is just where everything's going to be, and then you just have it split into the train, the valid, and the test. And in each of these folders, it's just the images. It's just the straight up images. So yeah, you want to split your image data up into the train, valid, and testing directories.
Oh wait, no, I thought you.
I'm
so I thought
sorry.
you also had the class
Sorry,
directories. You're good.
I lied. This is really hard to do without
Wait,
visualization.
let's just go here.
Yeah.
Let's go show them the files here.
There we go. There we go. Thank you, Kyle.
Yeah.
So yeah, you have like the test directory, and then you have the classes. So, you have the adenocarcinoma images under the test/adenocarcinoma. The normal images under test/normal, and this is like a pretty intuitive directory structure for your images, where you have it split between train, valid, and test, and then you store each corresponding image in the corresponding class directory. And when you do this, PyTorch and TensorFlow kind of take care of making the sort of image dataset object for you. So yeah, once you have something that looks like this in your like directory or where your notebook is, it should work out of the box.
Yeah. So basically, you can take anything that's in folders like this, throw it in the thing, change where that folder is pointing to, and you can literally just go through this and train it yourself on whatever data set you want.
Yep. And actually, that's what we did, right? Because
Yeah.
first we did adenocarcinoma on CT scans, and then we did pneumonia or normal on X-ray images. So, we have something that has like test and then pneumonia and normal. So that's really why transfer learning is so useful. Okay, so I define transformation, and then I create the data sets. So this is just going through everything in the train folder, getting the class, because what this does is it gets the last thing in the file path, which is the label, and then append it to classes, and then I append all the train image paths, and then I do the same thing for validation and testing. And these are this is just a utility dictionary that tells you, if some which index corresponds to which label, since we're going to use it's going to predict a number rather than the label itself, so we want to correspond that number to a label. And then we create a data set class that takes the images and has the initialize, the length, and then the get item functions. Yeah, so what I think what's most important here is the get item. Basically, it loads the image from the file path, gets the label, applies the transforms, and then I'm returning the image object, and then the label, and then the file path itself. But yeah, this is like the basic way of doing transfer learning within PyTorch, or image classification in general. And then I create the data sets by specifying the parameters. And then I create the data loader. This is a PyTorch thing, but you load in the data set object and then the batch size, and then you have the data loader, which is what PyTorch uses for training. And so here's just an example of an image. And as you can see, here's the file path. Here's the dimensions of the feature batch it's in, and then its label, which is 3, which corresponds to adenocarcinoma.
Yeah, so this is the output from Resonant, right?
Not yet.
No, not okay.
Not yet.
Never mind.
And so now we're training the model, and so this is gonna take a lot to explain. This custom training loop, basically, it's from this tutorial provided by PyTorch, but basically, as you can see, what it does, it loops through the number of epochs, and then each epoch has a training and a validation phase, and it gets the loss and the things that has correct. And then this is what we use for transfer learning for the most part. What this is doing, this zero grad, is saying you're not going to train on the parameter weights. And I think, yeah, you need that to ensure that the base layer is frozen.
And the base layer being Resonant. So
Yeah, the base
so
layer
it doesn't
being
go back
Resonant.
into Resonant and change the
Change,
parameters
yeah,
that
the
they
load
have
weights.
trained on.
So, yeah, the training function is a bit complex, and there's a tutorial for it, but I'll go into the specific transfer learning part, which is actually really easy. So here, you instantiate the model, you just call a function, and you say that it's pre-trained. And so yeah, we're loading in the Resonant 50 model, architecture and weights. And then you define the number of features being inputted into your custom classifier head. And then you define the last layer, which is your custom classifier head. That's a linear layer with the expected number of features and n class outputs. In this case, with the CT scan, n equals 4, because we have squamous cell, carcinoma, large cell, carcinoma, adenocarcinoma, and normal. And then you put it onto a GPU or a CPU. Define the loss function.
Don't use a CPU.
Yeah, this is using a GPU.
Yeah, don't.
That's
actually not an option. If you use a CPU for this, don't.
Yeah, it's just really if you don't have a GPU.
Yeah.
But yeah, and then we define the optimizer to use for this transfer learning, as well as the scheduler that basically changes the learning rate as you train. And then this is the training loop. We train it for 25 epochs, and as you can see,
How long it took?
no, it doesn't.
That's tough.
Oh wait, no, it does.
Oh yeah.
It took 4 minutes or 5 minutes.
Yeah,
with the
but that's with a
GPU.
GPU. With a
Yeah.
CPU, it'll probably almost 10 or 20x
Yeah.
on a loop. So
But yeah, I want to emphasize that this cell is the basic transfer learning part, and it corresponds pretty well with what we did, like what the diagram is. You load in the base model and say that it's pre-trained. You specify the next layer, which is this linear layer, to have the number of features that is coming out of this base model. And then you specify the number of outputs that it's going to have for your task. So yeah, in 3 lines of code, you've done basic transfer learning. And yeah, that's the whole training loop for transfer learning. This is just a bunch of stuff that we did on our end for
yeah.
keeping track of like the accuracies and the confusion matrices. But yeah.
Yeah.
Any questions? Right,
Lost
awesome.
in the code. But yeah, I mean, that's pretty much all I mean, other than, I guess, oh, close. Okay, does it still have this? Yeah, okay. So now you can see what the results are on the testing set, actually. So this one here, I don't know why it's doing that, but I mean, it's normal anyways, so you can see it's kind of weighting normal things like on the outside-ish, inside-ish. Yeah, you can see I picked and choose which one to use for my presentation. You get roasted. This is the one I probably ended up choosing. Yeah, and then large cell. I honestly don't know what these things are. If anybody knows, can. No. Okay. Sick. We'll just believe, because it came out really well. But yeah, I mean, this one's probably. I mean, that's a weird looking heart. I'm not gonna lie. But yeah, essentially, this is what the results are, and you can come down here, and then you can, on the actual notebook itself, you can go to the links, and you can go and look through them yourself on the notebook. And we basically did the same thing here. We just replaced the folder names up here, and I actually so we had a very small validation set for this one. So I basically just like switched which folder it was at the beginning. Still works, it's fine, but just FYI, because I didn't want to have to like go through and change all the val to test. I was just like, whatever. But yeah, I mean, that's pretty much it.
Yeah.
You guys have any questions? Just let me know. Yeah. Sweet. Any questions? Yes.
When deciding which metric you want to use between the accuracy and the F1 thing you were talking about, what do you want to take into consideration when you choose which one you want to look at as like the best metric for how to verify your model?
Well, we trained ours. So a metric is just like explaining how performant the actual model is. So the most important thing, so a metric is kind of like saying over time how well it's doing. Whereas like a loss, so we actually chose a categorical cross entropy loss, right? Yeah, which basically just tells you, how do I explain this?
So basically, like, it's used for multi-class classification.
Yeah, it's specifically for multi-class classification, and typically when you're doing something like this, there's going to be like some sort of predefined loss for your. So like there's like certain types of machine learning. There's like classification, there's like segmentation, there's natural language processing, and typically all these different types of machine learning have one specified loss that is like standard throughout like the research papers on that one type of learning. So like for example, like in segmentation, something that's like a loss function that we would use is called an IOU, or like an intersection over the union. So the main difference between this and the other one is that in segmentation, you're basically defining a class for each pixel. So instead of having like, it's like a cross entropy for each pixel instead of a cross entropy for the entire pictures class.
Yeah. And to extend off of that, it's really like domain and task specific.
Yeah.
You know, if you have 1.2 million images of 1,000 classes, but you have an equal number of images in those, there's not much imbalance. But in the nature of medicine, right, as Jim pointed out, it's very common to have imbalanced data. So that's why accuracy may not be the best fit. And so when you consider the problem space you're working in, or even just what data set you're working with, like that's why Kyle did the ROC rather than just looking at accuracy. That's to fix the problem of imbalanced data sets somewhat. So yeah, there's a lot of different metrics you can use for measuring the performance of a machine learning model, but yeah, it varies across domain and across tasks. So yeah, just keep it in mind.
Hopefully that answers your question.
Yeah,
that answers
which context you're working within.
But the real answer is, if you want a metric, just add the metric, because it won't change anything. So just after every step, just add like say an F1 score, if you want to see how the F1 score is performing over time.
What exactly is an F1 score?
Jim.
Okay, so I think to truly explain this, I kind of need to like draw a diagram of the computer matrix. Okay, so can you raise your hand if you think you fully understand what a computer matrix is? Okay, so explain like.
Oh yeah. This is a confusion matrix.
Yeah.
Wait, Jim's. Yeah. Can you just point it towards him? No.
Okay, so when we have like a prediction, it can either be like correct or incorrect. And let's say that we're classifying things as like positive or negative. And so here, I'll say this is positive, this is negative, this is positive, and negative. So one of these axes is going to be the predicted label, and one of these axes is going to be the true label. And so let's just say you can do either order, but it's important you're clear on which axes is a predicted versus true label. So like, let's say this is the prediction. And let's say this is the actual. And then let's say that we have 1,000 examples. Okay, so we have 4 boxes in our grid here, and they need to add up to 1,000. And the idea here is, let's go cell by cell. So the first cell is where it's predicted to be positive, and it actually is positive. And let's say that there's like 800, or like let's say 700 of these. And let's say that if when the actual is a negative class, but it predicts a positive class, let's say this happens 50 times. When the actual is positive but predicts negative, let's say this is like 100 times. And then they need to add up to 1,000. So 700 plus 50, 750, 750 plus 100 is 850. This needs to be 150. Okay, so there's a variety of different metrics you can use. Does anyone know what the accuracy of this model is? So the accuracy is the number, it's like the ratio that it got correct. So which ones are correct?
850 or 1,000.
Yeah, exactly. So the correct ones are here and here. So add up the correct values and divide by the total count. And so this is 700 plus 150 over 1,000, which is about, yeah, as mentioned, 85%. So this is the accuracy. If you want to compute the F1 score, you need to compute 2 metrics known as precision and recall. And maybe how you can like pull up a formula. It's basically like the sum of a ratio computed from this vertical and this horizontal. It's like a ratio of true positives versus false negatives, sort of thing.
Should I just look up F1 score?
Yeah, sure. Look up precision and recall too. Yeah, that's perfect. Okay, so precision is number of true positives over number of true positive plus false positives. So true positive is when it's actually positive and you predicted positive. A false positive is when it's actually negative but you still predicted positive. And so those are represented by these 2 cells here. So what is what's precision here? True positive is 700. Right. True positive is 700. This doesn't work.
You have like 1 minute.
Okay.
Just like FYI.
700 plus 50. So the precision, this is the value. Maybe you can put that in the calculator too.
Yeah.
That's the precision.
$93.33.
93.33.
Yeah.
And for the recall,
0.4. Oh, sorry.
Recall's 0.4?
Yeah, I think exactly.
Okay, so the recall is...
Actually, no, it's 150 over 250.
Yeah. So it's 150 over...
Is that right?
Wait, really?
True positive?
True positive over true positive
Oh, wait,
is
no,
false
no,
negative.
never mind.
So true positive and a false negative is when it's actually positive, which predicts negative. So that's why it's called a false positive versus negative. It's a false positive if you predict positive, but it's not. So it's positive, like you say it's positive, but that's false. That's what's called a false positive. And same for false negative. Here, this is a false negative. And so recall we consider here, here, right? The number of true positives over true positives plus false negatives is 700 over 700 plus 100. So this is recall. And what is this value?
0.875.
0.87. Okay, 87.5.
Yeah.
And then for the F1 score, we just need to take
2 times precision times recall over precision plus recall.
Right. Okay. So this is a concept known as a harmonic mean. It's a mathematical thing, and you can look more into it if you're interested. But we'll just use the formula for now. And so 2 times precision times recall over precision plus recall is, I think there's like a lot of numbers you can put in the calculator.
Yeah.
Like
So
2 times precision, 93.33 times recall, which is 87.5 over, is it precision plus recall?
Over precision plus recall, yeah.
Yes, okay. So 93.33
Copy,
plus
paste.
87.5.
Mm, 0.903.
Okay.
Yeah.
This F1 score. Yeah, 0.9032. Okay, so these are just like a couple of metrics that you can use. If you want to understand it really well, I would recommend like working on an example for yourself of confusion matrix. But like these are metrics that are very often used in practice. And of course you can use like as many metrics as you want, right? The most popular accuracy, recall, precision, F1 score, and then there's the RLC curve, area under the RLC curve, and intersection over union. These are the main like metrics used. I encourage you to like look into them if you're interested in like evaluating your model's performance from a very objective standpoint at a variety of angles. Yeah, that's an example, a fully worked out example of F1 score.
Nice.
Hope that's clear.
Thank you, Jim. That was impromptu. We did not plan that. All right. I think that's it. Thank you guys for watching.
Yep.
Thank you guys for joining. Appreciate it. Have a good one, guys.
Thank you.
Yes.